Hello all of you. So, in the last lecture we have been discussing the canonical ensemble, that is the NVT ensemble, and we determined how can we find properties such as average energy, average pressure using the canonical ensemble. So, in today's lecture I will discuss like how the temperature is defined using the zeroth law of thermodynamics. What is the origin of that if we think in terms of the canonical ensemble. So, essentially what we have been talking about is that in the canonical ensemble you have systems which are having same number of molecules, volume and temperature, and there are A such systems in the ensemble. So, in order to define temperature, what we do is we first assume that there is not one system, but two systems which are in a state of thermodynamic equilibrium. That is to say that inside the ensemble you have systems A and B which are in close contact. By close contact I mean they can exchange energy, but they cannot exchange the molecules between them. So, they are in a state of thermal equilibrium, so as to speak. They can exchange energies, they can have same temperatures eventually once they reach equilibrium, but the number of molecules in A and number of molecules in B are constant for the ensemble. So, if I assume that, in that case now again I have A systems in the ensemble, but in each of these A systems you have system A and system B in close contact. So, essentially now we can talk about the energies of the system A and the energies of the system B, and just like we had different possible energy levels of system in the last example we have done, in this case again you will have different energy levels, but different for system A and system B, right. So, essentially you will have energy level of system A that are EJA, where J refers to different possible energy levels, and similarly energy level of system B are EKB, k equal to 1, 2 and so on. So, if I now am interested in writing the number of ways of distribution for this particular ensemble, the number of ways are equal to the number of ways in which I can distribute the energies in the A systems multiplied by the number of ways in which I can distribute energy in the B systems. And since A and B are always in close contact, the total number of A systems is equal to total number of B systems. So, we can write W A as something like A factorial by A naught factorial, A 1 factorial and so on, and similarly for system B again you will have the same number of systems, but the occupations will be B naught, B 1 and so on. So, A naught refers to the number of systems A with energy E naught A. A1 is the number of systems with energy E1A. Similarly, B naught is the number of system B with energy E0B, and we can have B1 as the number of systems B systems with the energy E1B and so on. So, now just like I wrote for the last example, in here as well we can write this A as the A factorial by the product over the j systems A j factorial and again A factorial by product over now the index k of b k factorial. In fact, we can also replace the numerator here by writing it as sum over A j factorial and the same thing for the B systems. Keep in mind that both the numerators are the same, but since I am taking care of constraints separately, therefore, I have replaced the numerator with the summation, right. So, even if we do not do that, we get the same result, but just to be rigorous, it is always a good idea to think of it in this particular way. So, now there are certain constraints here, and the constraints are if I sum over the A j's, this is equal to A, and if I sum over the B k, that is also equal to A. But now, when I look at the energies, now we have to add the energy of A and B, because they can exchange energies, although they cannot exchange molecules, they can still exchange energy. So, if I talk about energy of A and B in close contact, that we can write something like summation over j A j E j A plus summation over k B k E k B, and the entire ensemble can be again thought as an isolated system. So, total energy for the entire ensemble can still be assumed to be constant, that I am representing as capital epsilon. So, now I want to maximize W, that essentially is equivalent of maximizing ln W, but now the variables that we have are both the A j values and the B k values, actually the distribution of them in the ensemble. So, now since W is equal to summation over A j factorial by product over j A j factorial multiplied with summation over B k factorial by product over B k factorial, we can again use the Stirling approximation, and then the ln W will be summation over A j. Keep in mind that whenever I write summation over A j, the index is j. Whenever I write summation over B k, the index happens to be k. And this minus for the numerator, we will have the summation over A j ln A j plus summation over A j. So, basically again you will have cancellations, and then you will have the same quantities for the second expression, that is we will have summation over B k ln summation over B k minus summation over B k minus summation over k B k ln B k plus summation over B k. Again we will have the cancellation, and therefore, we can write ln W as summation over A j ln of summation over A j minus summation over j A j ln A j plus summation over B k ln summation over bk minus summation over bk ln bk, and then we have certain constraints here that we have written. So, first constraint is summation over aj minus a is equal to 0. Second constraint is summation over bk minus a is equal to 0, and the third constraint is summation over aj eja plus summation over bk ekb minus e is equal to 0. So, now if I do the minimization has to be done with both aj and bk variable. However, keep in mind that the constraints that are there are defined for both the variables together, right. So, we did not think of them as two separate types of variable, and therefore, we should think of two different constraints, because in the constraints, since the variables come together, we should think of both aj and bj as forming a list of variable. So, whatever minimization that we are doing, in that the constraints will have the same Lagrange multiplier, right. So, if it is not very clear, you can think of this as equivalent of variables a naught, a 1 and so on, and b naught, b 1 and so on. Mathematically speaking, a naught, a 1 and b naught, b 1 are still the variables of the same equation. Although they refer to different systems in the particular example, but mathematically speaking, there is no difference between the a variables and the b variables. So, therefore, the corresponding Lagrange multipliers for the constraints are going to be the same. So, that means that I can write the maximization problem as dou ln w by dou aj minus some Lagrange multiplier multiplied with dou g1 by dou aj minus some other multiplier multiplied with dou g2 by dou aj minus some other multiplier dou g3 by dou aj, this equal to 0 for all values of aj. And similarly, we can write for bk, and the point to remember is the Lagrange multiplier has to be the same, because as I said, we can combine the two variables together and they become the variable for the entire equation, right. So, there is no difference between the variables as such. So, we should not have different Lagrange multipliers for the same constraints. And that is particularly important for the last one, because in here both aj and bk come together. So, this then becomes the same thing, but with respect to bk. For all values of bk. So, now I can write the dou ln w by dou aj looking at the equation that we had here, that is equal to summation of aj over aj plus ln of summation of aj minus aj by aj minus of ln aj, and then we have terms containing bk in the equation, which will not have any derivative with respect to 0 aj, and therefore, those terms will not appear. So, therefore, we will have cancellations here. This is equal to minus of ln aj by summation over aj, which we can write as minus of ln aj by a using the constraint that we had. So, now dou g1 by dou aj, going back to the equation for G1 that we had here, that will be equal to 1, dou G2 by dou Aj is equal to 0, because in the expression of G2 we did not have Aj appearing, and dou G3 by dou Aj, going back to the equation right here, will be equal to Eja. So, therefore, I can write the maximization problem dou ln W by dou Aj minus lambda 1 dou G1 by dou Aj minus lambda 2 dou G2 by dou Aj minus lambda 3 dou G3 by dou Aj is equal to 0 as minus of ln Aj by A minus lambda 1, and we will have 0 in the second term, minus lambda 3 Eja, which gives me Aj is equal to A exponential minus lambda 1 minus lambda 3 Eja. If I do the same stuff for the variables Bk, the equation we will have is Bk is equal to A exponential minus lambda 2 minus lambda 3 Ekb. Now, let us look at these two equations. So, we have found Aj as exponential of minus lambda 1 minus lambda 3 Eja, and Bk as A exponential minus lambda 2 minus lambda 3 Ekb. Let us first use the constraints. So, summation over Aj is equal to A. This gives me the value of exponential of minus lambda 1, and that is equal to 1 over summation of exponential of minus lambda 3 Eja, and similarly for Bk we can find exponential of minus lambda 2 as 1 over summation of exponential of minus lambda 3 Ekb, and if I put that in here, that is equal to A exponential minus lambda 3 Eja divided by summation of exponential minus lambda 3 Eja, and this is equal to A exponential minus lambda 3 Ekb by summation over exponential of minus lambda 3 Ekb. So, if I look at this particular expression here, we notice something, that this Lagrange multiplier is the same in both these equations, right, and the denominator is similar to the partition function we defined earlier, but now the partition function is different for systems A and for systems B. The other way to think about it is we can define the probability for a system A to have energy Eja as something like Aj by A, and that is equal to exponential of minus lambda 3 Eja by Qa, and the same thing we can do for the B systems. So, I will do the probability of having the state E j and for systems A and probability of having state E k b for systems B, they are themselves different, but both of them are essentially proportional to something like the Boltzmann factor we had, that is exponential of minus of something, and that something contains the same factor lambda 3. So, therefore, whenever the systems are in a close contact, there is something that is common between the system, and that something in this case is the Lagrange multiplier lambda 3. Which is same in both these cases. It turns out that we can identify this lambda 3 as beta, that is equal to 1 over k b t, and this exactly is the statement of the zeroth law of thermodynamics. So, whenever two systems are in close contact, there has to be something that is common between the two systems, and that something relates to the temperature. This is the definition of temperature. Whenever there are two systems in close contact, there has to be a quantity called temperature that will be same when the systems come in a state of thermal equilibrium, and that is the definition of the beta variable in thermodynamics. So, therefore, we can now write finally P j a as exponential of minus beta E j a by q a and P k b as exponential of minus beta E k b by q b. And naturally, whenever we talk about this probabilities, we are talking about two systems in close contact. So, the probabilities should be of the system A having some energy and system B having some energy. So, what is more relevant here is a probability of the form P j k, that means that the system A has energy E j a and system B has energy E k b, and that is equal to the product of these two probabilities. That is exponential of minus beta E j a plus E k b divided by q a multiplied with q b. So, this completes the derivation of temperature. There is another way to look at the same problem that we will discuss in the next lecture.